So yesterday we discussed about the BCD and through the PPT itself I already explained about the number conversion, so that how you are going to be converting a binary to a decimal and decimal to binary and a fractional number. Okay, so everything we have been discussed through the PPT itself yesterday's class. So now the thing is that here Boolean algebra as well as the De Morgan laws, we already discussed that. The next one is the logic gate. So you have to know about the what do you mean by logic gate here. Okay, so the logic gate, uh, which is going to be perform the Boolean operations, so that this is an electronic circuit and which is going to be control the flow of the information in the form of pulses here. Okay, the pulse should be either low or high. The low means 0, high means 1. That is the thing you need to understand. Okay, so the thing is that here in logic circuits, which may have n number of inputs, but it may gives you only one single output, that you can call it as a logic gate. Okay, any number of inputs, but it is going to be giving only one single output, that is called here logic gate. Okay, so so different types of ICs are also there, which are related to do these operations, Boolean operations. So integrated circuits are there. The circuit which may have 7433, 7402. Different types of ICs which are going to be performing these logical operations, either it is a AND gate or OR gate, NOT gate, whatever it may be. Different logic gates which may have its own ICs. Okay, so the thing is that here you need to verify the truth table also. When the signal is both are high, or else the any of the input which may have the high signal or else the low signal, both the inputs are low, both the inputs are high. How these operations which are going to be performed by these gates here, that you need to check out here. Okay, so the basic logic gates, I just want to show you these operations with respect to the PPT itself. I just want to explain logic gates, logical operations itself. You need to know about that. And the thing is that here, uh, the basic logic gates, which are the uh, AND gate, OR gate, as well as the uh, what do you say, NOT gate. Okay, logic gates. So I just want to share the PPT for the logic gates here. Better to wait, so that in a textbook itself it may have the so many what do you say, mistakes are there, printing mistakes are there, only printing mistakes, so that you need to correct it while the operation is going to be going on, whether it is a for uh, AND gate operation or else the OR gate operation and NOT gate operations. So there itself you need to check out these, so that uh, which is very uh, useful to us. That means if you are going to do this, which is very in the logic gates itself, it may have uh, four operations. That means if two inputs are there, four operations output. How it is going to be generated based on the gate here. AND gate, OR gate, NOT gates, basic logic gates. By using these gates itself, you need to find out that what are the construct the universal logic gate. What do you say? Universal logic gate as well as the XOR gate is also. Okay. So that is the thing you need to find out here. So uh, I am checking itself that logic gates PPT. Yeah. I just want to share the PPT so that you can easily go on. Yeah. Logic gates, basic logic gates. Okay. So logic gates which are used to process the digital signals, which are called the logic gates, and the gate is a digital circuit which may have one or more input voltages, but it may gives you only one output voltage. So what are the basic logic gates? AND gate, OR gate, and NOT gate. So that these gates you can easily connecting in different ways to build a new circuit, and it has to perform the other new arithmetic operations, and which are also associated with the human brain, the functions. So these logic gates are two types. One is the combinational, and another one is the sequential logic gate. So these combinational gates, the output at any instant which is going to be depends upon the input at that particular instant. So what are the example for the combinational AND OR gate, NOT gate, NAND, NOR, XOR? These are comes under the combinational gates. So whereas in the case of these sequential gates, the output which is depends upon the order or sequence, okay, which the inputs are applied. Example, see the flip-flops, counters and resistors. So for the analysis of the digital circuit, designing of the digital circuit, symbolic logic, which were invented by the uh, Boolean, that is Boole. You can call it as a Boolean, and that's what it is named as a Boolean algebra. Okay. So in this Boolean algebra, according to the Boolean algebra, only two possible states which are to be executing. One is the true or false. Okay. So the Boolean algebra only three operations are going to be possible. One is the OR gate, which may gives you the output of the uh, input of the variables which are going to be adding. That is related to the OR gate. The multiplication which may gives you the AND gate, and the complement which may gives the NOT gate. Okay. So you can go through the OR gate here. When the two or more inputs are there, you can see here A and B. Two or more inputs are there, only one single output which is going to be giving out here. The output of the OR gate. When the output of the OR gate which is going to be gives high, you can see here this is the 5 volt DC supply, and there is a bulb is there, and these two are the switches are there. One A and B two are the two switches which are connected parallel here. Okay. A or B, two switches are there. So this circuit I am going to be explaining now itself. You can see. Yeah. So here two switches are there. What are these? A and B are the two switches. Okay, these are connected parallel. So this is the 5 volts DC supply. DC. This is the bulb or lamp. So here the 5 volts DC supply is coming out, and this A is open here, and similarly B is also open. The negative terminal of the battery which is connected to the lamp, and here if it is open here, both the cases are open. There is no power which is reaching towards the to the bulb here. So in this condition, the bulb doesn't glow. Okay. Here one thing you need to remember, 0 means slow, open, okay, doesn't glow, and off condition. 1 means high, closed, glow, on condition. Okay, these are the conditions you need to understand. So in this 0, 0, both are low. Either bulb is going to be glow, doesn't glow. Why? Because of the power here itself. The switches are open means it is not going to be reaching towards the bulb. Okay. Next, A open, B closed. B closed here. Okay. A open, B closed. So that we open means here the power may not goes towards the bulb. But the thing is that here there is a way to reach out the bulb, the power which can reach out towards the bulb. So in this case, the bulb will glow. Glow means 1. Is it clear? And the other condition is that A is closed, B is open. So that in this condition, the bulb will glow. If both the switches are closed, both switches are closed. In this condition, the power is only 5 volts. So you need not to be understand that here double switches are closed means double power which may reach it towards the bulb. Okay, don't think like that. Here this is on condition, this is also on condition means only the input source is 5 volts. Okay, there is no 10 volts of the power reaching toward the bulb. Only 5 volts is there. So that both the switches are closed means here the power may reach towards in this direction or else in this direction parallel. The output should be like this. So that in this condition also bulb is going to be like that. You need to explain. Okay. So with respect to this diagram or else with respect to the diodes are also going to be uses. The diode, junction diode. Okay. So in circuit itself, in textbook, they may execute the diodes here. So you need to connect it. 2 diodes you are going to be utilizing. The source there itself, it is required 5 volts DC supply. Okay. Through the resistors, we are going to be connecting and we are taking. Okay now. Yeah, here you can see the diodes are there. So the diode voltage VA and other diode voltage is VB. Okay. So here the diode is D1 and the diode is D2. There is a resistance, load resistance is there, grounded here, and this is the V output voltage. Okay. So the input which may have the 2 inputs, VA and VB. V out is the output voltage. Here the symbol which can take it as a low voltage or else the high voltage. Low means 0, high means 1. Okay. Low means 0, high means 1. If the inputs are low, here is low. Okay. The low means low signal means the diode which is in reverse bias. Reverse bias, that is switch is opened here. Open means no current which is going to be flowing through it. So the output is also 0. Okay, 0 which is in reverse. If A is high, B is low. A is high, B low. A high means diode D1 becomes forward bias. 0 means reverse bias. Okay. The switch is enclosed. Then the diode, the neglecting diode forward resistance and the voltage drop across the load resistance. Then the output which is high. If A is low, B is high, the diode D2 becomes forward bias and act as an open switch. Hence the output is also high. Both the inputs are high. 1, 1. Okay. Both the inputs are high. So in this condition, the diode D2 becomes in forward bias, act as an open switch. Both the diodes. The more positive values of the, hence the R has been implemented. Next AND gate. A and B. Okay. A and B. So the output is A dot B. So here these two switches which are connected in series. This is the 5 volts DC bulb. So you know that open means 0, close means 1. Okay. Here both the switches are open. Here also open, here also open. Is that current is flowing through towards the bulb? No. So in this condition, bulb doesn't glow. A open, B closed. A open, B closed. In this condition also current is not reaching toward the bulb. Next, A closed, B open. A closed, B open. Okay. A closed, B open. So A closed, here A closed, B open. Here the power is not in this condition also the power, the bulb doesn't. When the both the switches are closed, current is reaching like this. In this condition, the bulb will close. So the diodes, two diodes, when the A is on high, that means 1, B is 0, low. High means diode D1, which is in reverse bias. Okay, in this condition. Act as open. Open means it doesn't conduct any current at all. Then diode D2, which is in forward bias, and it is going to be acting as a closed switch. And the output should be low. Okay, in this condition. If A is low, B is high, diode D1 becomes forward bias and act as a closed switch. Diode D2, which is in reverse bias, act as an open switch. The output is low. If all out inputs are 0 and the diode becomes forward bias, then it is going to be acting as an open switch and the output is low. When all the inputs are high, then the diode becomes in reverse bias, hence it is going to be act as an open switch. The output is become high. Okay, so You need to go through like this. Next is the NOT gate. You can see if A is there, A bar. Okay, this is A bar. If 0 is there, 1. 1 is there, 0. See here 5 volts DC supply. So here a switch is connected between the two terminals of the wire. So that is the case. So you need to go for it. If A open, then the bulb glow. If A is closed, A is closed means plus and minus are going to be short circuited. In this condition, doesn't go. Okay. If A is closed, doesn't go. If O open, then the bulb will go. A bar, you need to say that. That means an inverted version of the input as its output. That's what it is called as an inverter. If the input variable is A, the inverted output is known as not A. And this is also known as A bar. Here there is an inverter. NOT gate is an inverter because the output opposite to the input. That's what it has, only one input and one output. So V in is there, V output is there. Here there is a transistor. Okay. The output must be low if the input is high. Also, the output must be high if the input is low. So, in this condition, if the input is low, the parameter which is going to be chosen here, so that the output, that is V saturation. What do you say? V saturation. Also, if the input is high, the parameter chosen, so that the output is low. If the input is low, the transistor which is going to be act like a open switch, hence the output is low. If the input is high, the transistor acts as a closed switch. Then the output is high. Okay. Next, De Morgan's theorem. These are the basic logic gates. Now we have to discuss about the De Morgan's theorem. That is the first law which is indicating here the complement of the product of the two or more variables, where it is this one. The complement of the product A dot B of the two or more variables is equals to the sum of the complement of the individual variables. Sum of the complement of the individual variables. Okay. So this is nothing but a bubbled NAND gate is here, left hand side. A dot B whole bar means NAND gate. A bar, B bar. This is a NOT gate here. This is also another NOT gate. A bar, B bar. So A bar plus B bar, which is nothing but OR gate. So NOT gate which is followed by OR gate. A bar plus B bar. So this you can, if NOT gate which is followed by OR gate means that is a bubbled NOR gate. Bubbled OR gate means you can see here. Here there is a bubbles. A bar plus B bar. This is the bubbled OR gate. Okay. Bubbled OR gate should be like. So if you want to check out this is the LHS value. This is the RHS. So for the truth table itself 0, 0, 0, 1, 1, 0, 1, 1. What is A dot B whole bar? What is A dot B? A dot B is 0 dot 0, 0, 0, 0, 1. A dot B. A dot B whole bar means 0 bar is 1, 1, 1, 0. Next A bar plus B bar. A bar is this one, B bar. By adding 1 plus 1 is 1. 1 plus 0, 1. 0 plus 1 is 1, 0. So you are going to be equating this with the values of this. This is LHS, RHS. Next, second one is the A dot B whole bar equals to A bar dot B bar. That is the complement of the sum of the two or more variables, which is equals to the product of the complement of the individual variables. A plus B, OR gate, which is followed by NOT gate. OR gate, which is followed by a NOT gate, is NOR gate. This is the symbolic representation. This is LHS. What is the RHS? Bubbled AND gate. Okay, NOT gate followed by AND gate. That is A bar dot B bar. So this is the symbolic representation. So here also LHS is this one, RHS. 1 triple 0, 1 triple 0 by applying these conditions. Okay. This is the NAND gate here. AND gate followed by NOT gate. NOT gate is nothing but a NAND gate. This is the supply, 5-volt supply. Into switches which are short circuited here. In parallel, they have been connected. A open, B open. Then the bulb will glow. If A is closed, B is open, the bulb will glow. If A is open, B is closed, the bulb will glow. If both the switches are closed, the bulb doesn't glow. Okay, this is the NAND gate. Next is the NOR gate. NOR gate is nothing but a OR gate, which is followed by NOT gate is nothing but a NOR. Okay, OR gate which is followed by NOT gate is nothing but a NOR gate. So OR gates are there. Parallelly, the switches are connected. If A is 0, B is also 0. That means A is open, B is also open. Then the A plus B full bar, which is nothing but a 1. The bulb will glow. Either any of this which is going to be closed, the bulb doesn't glow. Both the switches. Why? Because of short circuiting. Okay, that is belongs to the NOR gate. Next is the XOR gate. XOR. This you can call it as a exclusive OR gate. Exclusive OR gate. So exclusive OR gate symbol should be like this. A XOR B. This is the exclusive OR. What do you say A XOR B? Like that. So what it is A B bar, B A bar. Okay. So A B bar. That means how many gates which are present inside the XOR gate? A B bar means, first of all, write it down. Bar means NOT gate. How many are there NOT gates? 2 NOT gates. And one OR gate is there. Plus is there. One OR gate. But between A dot B bar, B dot A bar, 2 AND gates are. So 1, 2 AND gates, 1, 2 NOT gates, 1 OR gate. Total how many gates are there? XOR gate itself it is having 5 gates. Total 5 gates are there. Okay. This is A and here is B, B bar, A, B bar. And that is B bar. So B, A bar. This is B, A bar. So by adding means OR gate. So in XOR gate, any of the 2 inputs which are having either low or high, the output is 0. Okay. If both the inputs are either high or low, output becomes 0. Or else any of the input is having high or low, the output is high. That is the advantage of the XOR gate. Okay. Next, half adder, full adder. This half adder is a digital logical circuit, and which is going to be implement the addition of numbers. Many computers and other types of processors, adders are going to be using to calculate the addresses and such type of operations, table indices, arithmetical logical operation unit. And these are classified into 2 types. One is the half adder and the full adder. Half adder which may include the XOR gate and AND gate. XOR gate which may gives the sum and AND gate gives the carry. Next, the half adder has only 2 inputs. Whereas if you want to get if you want to have if the gate is having more than 2 inputs, there itself a full adder is needed. Okay. So in full adder, two XOR gate, two operators are there. These are one is the XOR gate and the gate. By adding, you may get it as a full adder. Operator sum and carry, which is going to be generating. Sum as well as the carry. You can see sum and carry. So exclusive OR gate, exclusive which may gives the sum. Carry is the AND gate. What is the AND gate output? 0 0 0 0 1 0 1 0 0 1 1 is 1. This is the AND gate. The sum is only XOR gate. This is the AND gate. Okay. This is the full adder here. Hmm. This is a parallel adder. Okay. A single full adder which may perform the addition of two 1-bit member and 1-bit carry. Okay. So, but a parallel adder is a digital circuit and which is capable to finding the arithmetic sum of two numbers. And if it is greater than 1-bit length, and it is going to be operating in a corresponding pair of bits in parallel, and it is going to be consists of full adders connected in a chain. Whether whereas the output carries the each full adder is connected to the carry input of the next higher order full adder in the chain. So a n-bit parallel adder which is going to be requires a n-bit full adder to perform these operations. So for 2-bit number is there, 2 adders are needed. While 4-bit number is there, 4 adders are needed. And so on. So parallel adders normally incorporate carry lookup logic to ensure that carry propagation between subsequent stages of addition, and it does not limit addition limit. So carry out C1 is there. Full adder is there. This is the one first full adder, second, third, up to and so on. So these are the two inputs which may gives the carry sum outputs. Okay. Here the carry which is generating like this. This is about the 4-bit parallel add. So working of the parallel adder. A full adder, first full adder is concerned. Adding the A1 and B1 along with the carry C1. It is going to be generate this sum S1 and the carry C2 which is connected to the next adder of the in the uh, chain. So here the other full adder which uses this carry bit and add with the input A to B to generate the another sum. So the process will continue till the last full adder and it is going to be using the carry bits. So what are the advantages of the parallel adders or subtract? These are going to be performing the addition operation faster than the compared to the serial subadder. The time required for addition does not depend on the number of bits. So the output parallel is in parallel form. That is, all the bits are added or subtracted to the at the same time, and it is less costly. Next, disadvantages. Each adder has to wait for a carry which is to be generated from the previous adder in chain. The propagation delay which is found to increase with the increase in the number of bits in this. It is to be added. Okay.